All right, folks, let's get started. Welcome to lecture number 15. I'm actually recording this lecture for the second time. The first time it didn't go through for some reason, technical issues. All right, lecture number 15. In the previous lecture, we learned about static one hazard, and we did one example where we came up with, let me switch my screen here. We learned about the static one hazard, and we came up with a hazard-free design for it. The propagation delay, this tiny amount of delay in our digital systems, they can cause some kind of a glitches, meaning when the output is supposed to be 1, it goes down to 0 for a small amount of time, and then it goes back up. So what we learned in the previous lecture, was if you have two groups that are disjoint, this is a keyword here, okay? So let me go back here. Yeah. And they are disjoint, okay, vertically or horizontally, then there's a hazard between them. To avoid and eliminate the hazard, we add consensus term in the K-map as shown in blue. Okay, so if you look at this K-map right here, initially we had made two pair, you see in red, and notice there was a disjoint between this rectangle and this rectangle right here. Okay, and because these two rectangles were adjacent, we had to come up with another rectangle that would join the two, and therefore we were able to eliminate the hazard. So this was the key, removing the glitch from the system. Now we're going to learn about static zero hazard, which happens actually in the product of sum, so which is known as a static zero hazard. So let's start with the first example that we have. I'm going to switch back again. Okay, all right. So again, what are static hazards? Those are momentary glitches, or change in a logic level that should not have changed. Static one hazard, which we did yesterday, was basically the risk of a glitch in an output that should have remained one. Static zero hazard, on the other side, is a risk of a glitch in an output that should have remained 0. Okay, so our first example is actually on POS, on static zero hazard. I have a truth table right here, and then the first thing I'm going to do is actually going to come up with an expression. So here's is going to be my W, this is going to be my X, Y. Because this is POS, I'm looking at my max terms, which are right here. Okay, so I have 0 here, 4, 5, 7, 4, 5, and 7. Okay, my obvious choice would be to go with 0 and 4. And then 5 and 7. Again, just like we did in the previous lecture, we're going to do it two ways. One with the conventional way of getting an expression from K-map, and the other way would be getting a hazard-free design by adding a consensus term. Okay, so let's move on to the graph paper. Okay. Before we move on to the graph paper, let's get the equation real quick also. So F is going to be, for this one, is going to be x plus y and for this one it's going to be w bar plus y. Okay, remember you got 0 1 here, 0 0, 0 1, 1 1, and 1 0. So the common here was 1, which is y bar right here, and then here vertically we got w bar here, so I got w bar. So x plus y, because it's the product of sums, so it has to be end with these two sums. And now that we have the equation, we're gonna get a timing waveform for it. Okay, I'm gonna rewrite the expression here so I don't go back and forth to that page. X plus y w bar plus y bar. Also, initially the situation is that we have initial conditions. We got w equals to 1, we have x equals to 0, and then y is equals to 0, and then we have there's a transition. Y goes from 0 to 1. Okay, y goes from 0 to 1. Okay, all right, so here I'm gonna start working on my timing waveform. Initially w is 1, so it's 1 all the way. Okay, remember this is 1, this is 0. I'm gonna move on to x, which is also 0, so it's gonna be 0 all the way. Okay, got 0 here, and then we have y, which was initially it was 0, but then it goes to 1. Okay, all right, awesome. I'm now going to work on this expression, but before I work on this expression, I'm actually going to split it and work on w bar first. So omega bar, I keep saying omega, w bar, because it's 1, so it's going to be 0 all the way. Okay, all right, I have then y bar. Y bar is 0, so the invert of that would be 1. Okay, and it would be 1 till it gets here. Now here the logic changes from 0 to 1, which would mean there is going to be a delay here, a few nanoseconds delay, and then it goes to 0. Okay, so this right here okay, a delay, and let's say we keep the delay same for all the gates. Let's say we have a 2 nanosecond delay. Okay, now that I've got w bar plus w bar and y bar, I'm going to work on w bar plus y bar. So w bar plus y bar. Basically, I am taking these two and then ORing them. So any of the input is high, the output is going to be high. So clearly the output is going to be high until I get to this right here. Here again, the logic goes from 1 to 0, which would mean it's going to stay 1 for a little amount of time, and then it goes to 0 because both are 0. This is 0, this is also 0, and it's going to stay 0. Okay, so again we have a small delay here. So this is going to be a 2 nanoseconds delay. I'm now going to move on to this expression right here, x plus y. It's y. I know X is 0 all the way, Y is this right here. So starting from here, it's 0 all the way till it gets here. This is when the Y goes from 0 to 1. There's a small amount of delay, and then output goes 1 because it's an OR. So we have another delay here, and say this is again a 2 nanosecond delay from an OR gate. Okay, and then the final expression F, which is basically these two terms ending. So I got these two terms right here, and they're ending together. Okay, so both inputs are high, output is going to be high. Okay, all right, so it's 0 until it gets here. Here logic goes from 0 to 1, and here logic goes from 1 to 0. Okay, so you see there's a gap right here. There's a gap right here, and for that very small amount of time the logic is gonna go up because both are going to be high, and then it goes down because both are set to 0. Okay, this is what we know as static zero hazard. Okay, this is something to understand, that when we had these two timing waveforms and they were ending together, when both inputs are going to be high, the output is going to be high. So we started off here because this was 0, and it was 0 all the way till here. Then the logic goes up, and there's gonna be a little delay before it goes up, but then the logic is 1 here, and then the logic goes from 1 to 0 after a certain amount of time. Until then it stays 1, and then it goes 0. Okay, so this is what we know as static zero hazard. And also sometimes it is also referred as glitch 1. Okay, there are different terminologies used. Okay, now we're going to do the same thing here. We are going to come up with a hazard-free design, and how we do that, we're actually going to look for adjacent rectangles where there is a disjoint. Okay, and if you notice here, there's a disjoint between these two rectangles. So if I make a pair here, now I have connected those two rectangles. It is going to add an extra term in my expression, but I would be able to eliminate the glitch. So the extra term would be, so here you've got W bar plus the common here is 0, so you got X here. Okay, so now your F is actually F, I'm going to rewrite over here, X plus Y, W bar plus Y bar dot W bar plus X. Okay, and remember, this is with the consensus term. This is your consensus term. Okay, if you try to come up with a logic diagram for it, so you got three OR gates. Okay, and then you got X, Y here, you got W bar, Y bar here, and you got W bar, and then you got X here. Okay, and this is your F right here. Okay, notice it's a two-level logic. So this is your level 1. Okay, this is your level 2. Okay, the more levels you're gonna have in your logic diagram, the more delay you're gonna have. Okay, so say for a 3-level or 4-level logic circuit, the propagation delay is going to be a lot more compared to a logic diagram that has 2 levels. Okay, so basically you have added this part of your circuit, but then you avoid a glitch. Okay, so I'm going to add this consensus term to my timing waveform and see if I can eliminate the error. So I'm going to move my F2 over here at the top. Okay, this is my new consensus term right here. F, so it was initially 0 for 2, roughly. It goes up and then goes down for a very small amount of time. The consensus term is going to be over here, which is W bar plus X. Okay, W bar is 0 all the way. Okay, X, oh sorry, W bar, yeah, correct, W bar is 0 all the way, X is 0, so this would mean it would be just a straight line. Remember, this is 0, this is 1, this is 0. Okay, and now this new F, the one with the consensus term, okay, basically you take these two and then end them, correct? Okay, so any of the input is high, not any, both of the inputs are high, output is going to be high. But because W bar X is 0 all the way from here to here, the output is actually going to be 0. So even though there is a glitch in the system, but it doesn't reflect on the output function. Also notice that the consensus term that you came up with is actually dependent on Y, which is the variable that is changing from 0 to 1. And because it's you don't have that variable in this expression right here, so it doesn't have an impact upon the output, but it does help us to eliminate the error. Okay, I want to do one more example, and I'm not going to do the timing waveform for it, where we just want to drive an expression, a static 1 hazard and a hazard free design. Okay, again, because we are doing static 0 hazard, so we are doing product of sum, so basically looking at the max terms. Okay, so say you have 0 here, 0 here, 0 here, 0 here, 0 here, 0 here, 0, 0, 0, 0. Okay, most people would agree that we can make this chord right here at the bottom. Okay, we can make another chord right here at the bottom, and then we can wrap around these two at the top on the sides. Okay, now let's get an expression for this. Again, here you got Wx, y, z. Okay, let's get an expression. You had 0, 0, 0, 1, 1, 1, 1, 0, and then 0, 0, 0, 1, 1, 1, and 1, 0. For this chord at the bottom right here, the expression is going to be W bar plus X. Okay, for this chord right here, the bottom, the common is 1, so which is W bar plus Z right here, common is Z bar, and then we have this chord right here, the common is 0, which is Z, and then on the vertical axis we got common 0 W, so W plus Z. And because we know that this rectangle is connected with this rectangle, however, this rectangle is not connected to any of these. So there is going to be a glitch, and one way we can avoid that glitch is actually by making this chord right here. Because this was adjacent to the ones at the bottom on this on the edges, we can add another consensus term, and then we can avoid an error. So the hazard-free design would have an expression, these would be the same. And then the expression for this would be, here the common is 0, so you get x here, plus, and here you got common 0 also, so that is z, x plus z. Okay, this is your consensus term right here.